Welcome to this lesson on number sequences. By the end of this video, you will be able to identify different types of sequences, describe them using term-to-term rules, and derive the formula for the nth term using Tn notation. Our main goals are to recognize and explain term-to-term rules and find the nth term for linear, quadratic, cubic, and exponential sequences. Let's start with the basics. A sequence is just a list of numbers that follow a specific pattern. Each number in that list is called a term. Take a look at this sequence. To find the next number, we look at the difference between the terms. Notice that we add 3 every time. This is what we call a term-to-term rule. In this case, the rule is simply add 3. Because the difference is constant, we call this a linear or arithmetic sequence. Now, describing a sequence one step at a time is useful. But what if I asked you for the 100th term? Adding 300 times would take forever. This is where the nth term formula comes in. We use the notation t subscript n to represent the general rule for any position, n, in the sequence. In our previous example, when n equals 1, the term is 5. When n equals 2, the term is 8. For linear sequences, the nth term always looks like something times n, plus or minus a constant. Since the difference was positive 3, our rule starts with 3n. If we plug in n equals 1 3 times 1 gives us 3. But our first term is 5. How do we get from 3 to 5? We add 2. So, the nth term is Tn equals 3n plus 2. You can check this. For the fourth term, 3 times 4 is 12 plus 2 is 14. It works perfectly. Not all sequences change by the same amount each time. Let's look at a slightly more complex pattern. First, let's find the differences between these terms. The first differences are 4, 6, 8 and 10. These aren't the same, so it's not a linear sequence. But look what happens when we find the difference of the differences. The second difference is constant at positive 2. When the second difference is constant, we are dealing with a quadratic sequence. The rule for the nth term will involve an n squared term. A quick trick for IGCSE is that the coefficient a is always half of the second difference. Since our second difference is 2, half of that is 1. So our sequence starts with 1n squared, or just n squared. If we subtract n squared from our original terms, we get the sequence 1, 2, 3, 4, which is just n. So, the nth term for this sequence is Tn equals n squared plus n. Quadratic sequences are a favorite in exams, so remember to check that second difference. Next, let's explore sequences that grow much faster. These are often cubic or exponential patterns. You can identify a cubic sequence if the third difference is constant. Consider this cubic sequence. 2, 9, 28, 65, 126, and so on. Let's analyze the differences for this sequence. The first differences are 7, 19, 37, and 61. The second differences are 12, 18, and 24. And the third differences are constant at 6. Notice that the third difference is constant at 6. This confirms it is a cubic sequence, meaning the formula involves n cubed. By comparing the terms of n cubed to our sequence, we see that each term in our sequence is exactly 1 more than n cubed. Therefore, our nth term formula is t subscript n equals m cubed plus 1. Now, consider this different pattern. 3, 6, 12, 24, 48, and so on. Here, we aren't adding the same number, we are multiplying by 2 each time. This is an exponential sequence. In the general formula, t subscript n equals a times r to the power of n minus 1. In this formula, a is the first term and r is the ratio we multiply by. For our sequence, a is 3 and r is 2. So, t subscript n equals 3 times 2 to the power of n minus 1. So, for exponential patterns, look for a constant multiplier rather than a constant difference. Let's put everything we've learned into practice with an IGCSE exam-style question. These often combine different types of sequences in a table to test your ability to switch between methods. Here is a table showing the first 4 terms of 3 different sequences. We need to find the nth term for each. For sequence A, we find the first difference. 11, 7 is 4, 15 to 11 is 4, and 19, 15 is 4. It is linear with a difference of 4, so it starts with 4n. When n is 1, 4 times 1 is 4. To get to 7, we need to add 3. So, for sequence A, t subscript n equals 4n plus 3. Now look at sequence B. These numbers should look very familiar to you. 1 squared is 1, 2 squared is 4, 3 squared is 9, and 4 squared is 16. This is simply the sequence of square numbers. T subscript n equals n squared. Finally, let's look at sequence C, 7, 15, 31, 63. The differences are 8, 16, and 32. This isn't linear or quadratic because the differences are doubling. This suggests an exponential pattern involving 2 to the power of n. Compare this to 2 to the n. 2 to the 1 is 2, 2 to the 2 is 4, and 2 to the 3 is 8. Notice that our terms 7, 15, and 31 are very close to 8, 16, and 32. In fact, if we look at 2 to the power of n plus 2, wait, let's try another approach. Look at the terms of C again. 7 is 8 minus 1, which is 2 cubed minus 1. 15 is 16 minus 1, which is 2 to the 4, 1. And 31 is 32 minus 1, which is 2 to the 5 minus 1. So the rule for sequence C is 2 to the power of n plus 2, all minus 1. T subscript n equals 2 to the power of n plus 2, then minus 1. To finish our look at IGCSE questions, let's look at one final challenge that involves fractions. Sometimes a sequence is presented as a fraction, where the numerator and denominator follow different rules. Find the nth term of the sequence: 2 over 5, 5 over 10, 8 over 17, 11 over 26, and so on. When you see a sequence of fractions, the best strategy is to treat the top and the bottom as two completely separate sequences. Let's look at the numerators first. 2, 5, 8, 11. The difference is a constant positive, 3. Since it is linear, the rule is 3n plus or minus something. For n equals 1, 3 times 1 is 3. To get to our first numerator, 2, we must subtract 1, so the numerator is 3n minus 1. Now let's look at the denominators: 5, 10, 17, 26. The first differences are 5, 7, and 9. The second difference is a constant positive, 2. This means it is a quadratic sequence starting with n squared. Comparing n squared to our denominators, 5 is 1 plus 4, 10 is 4 plus 6. Wait, let's look closer. At n equals 2, 4 plus 6 is 10. At n equals 3, 9 plus 8 is 17. At n equals 4, 16 plus 10 is 26. The amount we add is increasing. 4, 6, 8, 10. This is actually a linear sequence itself. 2n plus 2. So the denominator is n squared plus 2n plus 2. Combining these gives us our final answer. T subscript n equals 3n minus 1 over n squared plus 2n plus 2. Remember, in your exam, always check your formula by plugging in n equals 3 or 4 to ensure it matches the original list. In this lesson, we have identified linear, quadratic, cubic, and exponential sequences. We used T subscript n notation and solved exam-style fraction and table problems. You are now ready to tackle IGCSE sequence questions. Good luck with your revision.